Hi, I'm Kerry Knight, Mike 0 Kilo Romeo Echo from Torbay Amateur Radio Society. Today I'm going to give you a presentation on antenna analyzers, which is basically a quick guide as to what to do with them and how to interpret the wealth of information that they can give us. We all use, or a lot of us use antenna analyzers quite frequently these days. For looking at our antennas and trying to decide whether they're matched to the transmitter that we're trying to use. Some of us have got more than one. So this gives us an insight into the sheer amount of information that we can get from an antenna analyzer or a vector network analyzer, although I'm not going to cover VNAs particularly in here because it's a slightly different presentation. The example I'm using here is the Rig Expert AA600, which is a very, very good, but albeit quite expensive antenna analyzer. Most of us amateur radio enthusiasts check our antenna simply by looking at the voltage standing wave ratio, or just the SWR. And if we see an SWR of 1:1 or as near as it can get, then we know that our antenna assembly is ideally matched to the transmitter. What that actually means is none of the power that we're transmitting is actually being reflected by mismatches in that circuit back towards the transmitter. That all sounds great, but what does it actually mean? Just before we get going, when we talk about testing our antenna, what we are actually doing is testing the whole assembly. So that's the cable connecting the antenna, coax or feed line or whatever you're going to use, along with any connectors, any baluns that might be in the circuit, as well as the antenna. When they're all working perfectly and ideally tuned, then we can normally ignore all of that lot because we know that it's perfectly matched. When there is a mismatch, however, we have to consider all of those components and what effect they have. And this is where antenna analyzers can help us to understand what's going on. In radio frequency circuits, we have a transmitter and we have an antenna, and we also have a connection going between those, which is coax or balance line or some other sort of feed line. And that coax, for example, has what's called a characteristic impedance, usually written ZO or Z0. And the characteristics impedance of a uniform transmission line, i.e. a regular piece of coax, is actually simply the ratio of the amplitude of voltage and current of a single wave propagating along that line. So it's a bit like Ohm's law. What it means is it's traveling in one direction, so it's not being reflected back from the other way, so it's a single line. Now the characteristic impedance is actually determined simply by the geometry and materials of the transmission line and not by its length. So a 1 meter length of 50 ohm characteristic impedance coax has got 50 ohms characteristic impedance, and 100 meters of the same coax has a characteristic impedance of 50 ohms. So it doesn't matter how long that is. We normally work with 50 ohm transmission lines because that's normally what the output impedance of our transmitter is. Now, sorry, characteristic impedance is a slight oddity. You can't just treat it as a resistance or an impedance per se. If we think about drawing this as a circuit, we'd have a transmitter with a source impedance connected to a transmission line with a characteristic impedance connected to a load with a load impedance. And if they were all 50 ohms, you would expect the transmitter with a 50 ohm source impedance to see both of those in series, i.e. 100 ohms. But actually we don't. We still see 50 ohms. So the transmitter sees 50 ohms even though it's got a length of a characteristic impedance in the middle, and the load also sees a source impedance of 50 ohms, and no matter what the length of that feed line is. Now there will be losses in there, but the impedance doesn't change. So that allows us to use, as long as the characteristic impedance is the same as our source and load impedance, it means that we can effectively ignore what's going on in that piece of coax. Now, amateur radio users normally use coax or transmission line with a characteristic impedance of 50 ohms. So as I said, we can normally ignore that effect for short lengths other than losses. But where our antenna is not perfectly matched to the transmitter, then we need to take into account the interaction of the coax, the antenna, any balance, any connectors which might be in that circuit. So this is too much to do in this presentation, but it will help you to understand exactly how to go about looking at what's going on in there. For a perfectly matched configuration, none of the transmitted power would be reflected back to the source. So we can say that this configuration has a reflection coefficient, which is capital gamma, that little R symbol, of 0. And if all of the power reflected, i.e. we've got a short circuit or an open circuit at the antenna end, then we'd have a reflection coefficient gamma of 1. Now the reflection coefficient, as we said earlier, is basically just the ratio of the reverse voltage over the forward voltage. So it's a reflected voltage and a forward voltage. But remember, they are complex values, so they have phase angle as well as magnitude. Now, the reflection coefficient it can be represented as the load impedance minus the source impedance over the load impedance plus the source impedance. Remembering again that these are complex values. And our good old voltage standing wave ratio is actually given by another very simple formula, which is 1 plus the magnitude of that reflection coefficient over 1 minus the magnitude of that reflection coefficient. And remember that R is complex, but the magnitude just means it's the magnitude without any phase consideration. Okay, enough theory. So measuring the standing wave ratio, which we normally do, is just one way. But for a more detailed look, we need to look at the reactance as well as the resistance. The antenna I used in the following slides is a simple 2m/77 antenna mounted on a magnetic mount just bunged on a table close by where I was doing. So first things first, let's look at the voltage standing wave ratio as displayed at 2 meters. Now this output from the rig expert shows us at 144.84 megahertz. The impedance of our antenna is nearly 80 ohms plus plus 0.11 J. So it's very nearly resistive at 80 ohms. This gives us a reflection coefficient of 0.23 with a phase of 0.16 degrees. And that then equates to a voltage standing wave ratio of 1.6. I must say in this case the magnetic mount was sitting on a wooden table and not actually on the top of my car, which probably accounts for the fact that the standing wave ratio is quite high. Now down in the left hand corner we can see it gives you a vast amount of information. The frequency that is the center point where we're looking, standing wave ratio at that point, the load resistance, the return loss, the impedance, the magnitude of that impedance, there are various other bits all the way down through there, which is a bewildering amount of information. So let's have a little bit bigger dig into some of those. So exactly the same measurements that we took earlier, but this time, instead of looking at the standing wave ratio, we're just looking at the phase angle of what we're seeing from the antenna analyzer. And we can see here that at lower frequencies we've got a phase angle which comes down almost in a straight line, but it's not, believe me, crossing the 0 line where we said earlier at 144.84 megahertz. So that means at 144.84 we're very, very, very close to a purely resistive load. This chart gives us the return loss, although that sounds quite a complex thing, it's not really, at the same frequencies and antenna that we checked earlier. The return loss is simply the difference between the transmitted voltage and the reflected voltage. So the more, the less reflected voltage you're getting back, then the higher your return loss is going to be. So the higher the better here. We can calculate the return loss directly from the reflection coefficient gamma. It's simply minus 20 log to the base 10 of gamma. So in this case, it's 12.76 dBs. So the difference between our transmitted power and our reflected power is 12.76 dB. Other plots that we can get give us the same information in a number of different ways. This one shows us the reactance as well as the resistance, along with the complex magnitude of that impedance at the same time, as you can see from the top right hand thing. So the left hand is still exactly the same, the bottom left hand corner is still exactly the same as we had earlier. So all we're seeing is the same information presented in a slightly different format. Now this chart, called a Smith chart, is another interesting way of looking at exactly the same data that we had earlier. Although it looks very, very complicated, it's not. Again, it's just a different way of looking at the same information. Now, the center of that circle that we can see in front of us with a little 0.1 next to it actually reflects a reflection coefficient gamma of 0. And the outside of the circle is a reflection coefficient gamma of 1. And then anything above the line means it's got a positive phase angle, and anything below the line means it's got a negative phase angle. So anything along that horizontal line on the middle means it's resistive. And then the distance along that line, so we can see here we've got a horizontal line that's got 0, 0.2, 0.51, 1 point something, and then 2 and 5. That's a magnitude of the impedance that we're seeing. Okay, so that in this case where we're resistive, it means that we've got no phase angle and a impedance of about 1.65 times what we've actually got, which is because we're seeing a impedance of 80 ohms instead of 50. So we can see here that the pink line, which is our trace, starts off at the top with a positive phase angle and then curves around, coming to cross that center line at about a 1.65, the 80 ohms, and then continues down in a curve with a negative phase angle. So we can actually see here how that antenna behaves as the frequency starts changing. What we'd ideally like to see is it crossing that point that says 1 on the center line, which means at one point we would be perfectly matched. Okay, last thing to mention, which is slightly different and is actually a completely different set of information that we're being presented here, is what a lot of antenna analyzers, including the rig expert, do these days, which is called a time domain reflection analysis, or TDR mode. When we talked about reflected power, we can simulate that, as you can see with that little moving graphic, as we send a single pulse down the line and it hits a mismatch. Some of that power is reflected and goes in the opposite direction. Some of that wave continues and gets transmitted out from the other end, so you can see how that actually works. But as you can see, if you watch this, from there to there is actually a time delay, and that's based on the amount of time it takes for that pulse to get from our measurement device to the mismatch and back again. There's a mismatch and we're back at the transmitter. Now if we know the velocity factor of the transmission line that we're using, so for RG58U that's about 0.66, we can actually calculate the distance to where that mismatch is just by looking at the reflective voltage back. And that's what the TDR mode of an antenna analyzer does. So I just disconnected the antenna from the end of the magnetic mount and actually produced the following chart. Now, in this one, horizontally, the left-hand side is the source, so that's my rig expert, and time, or distance in this case, goes along the horizontal axis. As you can see, we've got length meters at the bottom. Now we've got three bits in here. One is an impulse response, as if we were sending just a single pulse of information down. That's the blue line. And the green one is a step response. And then from that we can actually calculate what the impedance at the point of that mismatch would be. So for our blue line, unfortunately you can't quite see it at where that single crossing line is in the middle there. Actually goes at 0 as near at, and then pips up and goes almost up to the 1 point before going back down to the 0 again. And that point there, which is actually 3.65 meters, you can see that all of the power, i.e. the 0.1 of that power, is being reflected back, which you would expect if you've got an open circuit at the other end or a short circuit at the other end. So from the blue line we can't actually tell what's going on. Okay, in fact we can, but it's more easily to understand what's going on there when we look at the step responses and the impedance responses. So in the step response we can see that it goes along, and then it doesn't matter what happens after that point at 3.65 meters, all of the power is being reflected. And then for the impedance, we can see it goes down from a very low impedance, which is where we were, and then goes through that point at 3.65 meters up to high. So we can tell that we're going to actually an open circuit condition there. If we were a short circuit, then you find that those two charts would be the other way up, so it would actually bounce downwards, not upwards. So by looking at those graphs and those particular chases, we can actually understand a lot more about what's going on. So this one shows you what we can see. For an open circuit, it would be a positive transaction going up, whereas for short circuit, it would go downwards. So we're getting a negative reflection rather than a positive reflection. And we can also say what happens if we're not actually open circuit, but we've got a load which is higher than our source impedance, and actually the reflection goes up but not all the way to 1, or similarly for a lower impedance goes down. We can look at discontinuities, we can look at what happens if we've got a capacitive problem at the other end or an inductive problem, and we can even look at what happens when we've got lossy cable, i.e. a slowly increasing reflection as we go along, or a cable that hasn't got a characteristic impedance is exactly what we want it to be, in which case we would see it being just above the 0 all the way along there. So we can actually do quite a lot by looking at this time domain reflection analysis, and it's very, very useful to be able to say how far away that problem is if you're looking for a kink in your coax or something like that. 3.65 meters is exactly the length of the coax that I've got connected to my antenna there. So I hope you've enjoyed the presentation and found what's been said in there quite useful. One thing I would say, a common mistake, is to don't choose too wide a frequency range. If you do that, which I've done in this one, I selected a huge amount of information from 0 to 600 megahertz. You'll see that you get so much information, you've got no idea what's going on, and it looks really, really difficult. So try and select a frequency range that's narrow enough and just encounters the frequencies that you want to use. Selecting too wide a frequency range just gives horrifically complex outputs. So this little chart in there is what happens if you try and do a Smith chart analysis and you've got a too wide a frequency range. And normally these would be curves, but I think I've just exceeded the capabilities of the rig expert for the number of samples that it does on that wider range. So we've got square lines, but normally that would just be a spaghetti of curves. So thank you very much. I hope you've enjoyed that, and goodbye for now.